Welcome. In this session, we'll explore the use of the Lagrange dual to solve a problem that's of size 3. For this session, suppose that our objective that has a size 3 argument is 1/2 of the transpose of the vector times a symmetric positive definite matrix times the argument. And our property function is, in general, that would be a vector. In our case, let's suppose it's a constraint 1 form times the argument minus a constraint constant, a constraint scalar. And here we'll have size 3 vectors. So suppose that our constraint matrix is a diagonal 1, 2, 2, and then we fill in the off-diagonal entries to be 0. And suppose that our constraint 1 form is 1, 1, 1. And suppose that our constraint constant is minus 4. Let's pause and let's think about what the geometry of this is. This is difficult to draw, and the reason is that this is now a diagram that has to be in 3D, and the level sets of this objective are ellipsoids, and the ellipsoids are aligned with the coordinate axes, and the first radius will be 1, the second radius will be 2, the third radius will be 2. So that means that it would be smaller if we drew an ellipsoid, it would be smaller in the first dimension and then larger in the other two. And this constraint, when applied, is a plane, and this 1 form is the transpose of the normal vector for the plane, and this is the offset of that. So what we're trying to do is we're trying to constrain an ellipsoid objective function with a plane in 3D. The way that we solve this is using our algorithm, and step 1 is our solution matrix B is the constraint matrix times the inverse of the objective matrix times the transpose of the constraint matrix. And in our case, when I work this out, and I encourage you to work it out separately, I get the value 2. Our step 2 is, because there's no q vector term in the objective, is that our solution vector is simply the constraint vector. So in our case, we'll write s as a scalar, and that will be minus 4. Our step 3 is solve the Lagrange equation. And some people will use a plural, I'll use a singular. For our problem, the Lagrange dual, which only has so in general, the Lagrange dual for an equality constrained optimization problem where the objective is a quadratic form, that Lagrange dual takes the form of 1/2 of the transpose of the multipliers times our solution matrix B times the multiplier vector minus our solution vector dot product with the multiplier vector. And when we set the partial derivative of the dual with respect to the multipliers to be 0, what we get is that the solution is our solution matrix times, in this case we only have one multiplier because we only have one equality constraint, and that has to equal minus s. And that means that our optimal multiplier is minus, so this will be minus 2 inverse times minus 4, and that is minus 1/2 times minus 4 is, I calculate that to be 2. And then our step 4 is, in general, an argument is minus the inverse of the objective matrix times the transpose of the constraint matrix times the multiplier vector. And here, what we have is our optimal argument is minus, let's write out this k inverse. So recalling that the inverse of a diagonal is the diagonal of the multiplicative inverses, that will be 1 over 1 is 1, and that will be 1/2, that will be 1/2. I'll put zeros for the off-diagonal entries, and the transpose of our constraint 1 form is the vector 1, 1, 1, and we multiply that by our optimal multiplier. And when we work this out, this will be minus 1, 0, 0. So that will be minus 1 times mu star. So that will equal minus 2. The next one is 0 minus 1/2, 0 times that. So that will be minus 1. And then that will be 0, 0 minus 1/2, and that will be minus 1. Let's take a look at what the primal solution would have given us. We would have had a 4 by 4 matrix, and the upper left would be the objective matrix, so that would be 1, 2, 2, and then I'll add in the off diagonals. Then this last row is our constraint 1 form, which is 1, 1, 1. Then we transpose that to be the vector 1, 1, 1. We always put a 0 in the lower right corner, and that times the minimizer and the Lagrange multiplier has to equal, in this case, it would be 0, 0, 0, minus 4. And when you do the matrix vector multiply, you can verify that this solution solves this problem. So, this is the end of the lecture, and what we've discovered is that persistently we can solve an equality constrained optimization problem by using the dual formulation, and we can do it quickly and efficiently.